Before that, Dr. Curson, oh well,
Yeah,
you mentioned nature and the brain. Are you
yeah.
familiar with the Nature Fix book by Florence
Oh,
Williams?
yes.
Yeah.
Yeah. I haven't read
Okay.
it, but I know about it. Yeah.
All right. Okay.
I should look at that before I do my presentation. Okay, all right. Oh, we are recording. Okay, goodness. This is our monthly colloquium. It is February 19th. And I have the pleasure and honor of introducing Dr. Douglas Fields. You should know that he is a neuroscientist and an international authority on brain development. He has worked in areas such as neuron glia interactions and cellular mechanisms of memory. He's currently the chief of the Nervous System Development and Plasticity section at the National Institutes of Health in Bethesda, Maryland, obviously. He has published so many papers. He's written a book, you can kind of see it behind him in the corner there, called Electric Brain, that I have been reading, and I can't put it down. I'm really enjoying reading it. He's done all kinds of things. He's been on ABC News Nightline. He's been in National Geographic. He's been on NPR. He's published in lots of different areas or lots of different journals in lots of different areas of neuroscience. So I am honored and pleased again to have him here talking to us about, and you can see the title of his presentation, From Hans Berger to Modern BCI and Modulatory Interventions. So thank you for being here.
Thank you for that nice introduction, for your patience and all of those things, but I can't work Zoom. No, I don't. You know, again, I do Zoom all day long every day. I don't know what happened, but it's good. So in my talk, I want to give you a broad overview of brain waves, go into their discovery, what they are at a physiological level, and how they're transforming our understanding of how the brain works, um, and their applications in health and in brain-computer interface. Now, this talk is intended for a broad general audience with no prior experience in the field, because I find that many people are unaware of the revolution in brain science that's taking place right now that I really think is going to transform medicine and change society in profound ways. Now, I know that many of you are familiar with a lot of this, and so I hope that the broader scope and the history will be of interest to you, but I didn't want to leave anyone behind and assume that uh, that you know all about EEGs, etc. So with that in mind, let me say that electrical activity can be detected in the brain, can be detected through the scalp, and it gives insight into neurological disorders and psychological conditions, and it reveals the capabilities of your individual brain. Yep, it's not running. There we go.
Make sure your mouse is on the PowerPoint, not on the Zoom, and then you could use your arrow keys or your mouse.
Yeah, the space bar doesn't work. Arrow key. Is this Zoom any different from the other
No,
Zooms?
no. So go ahead and take your mouse and click it onto, yeah, I see your mouse there. Click it.
Yeah, click
Yeah,
the
just
mouse.
click it.
It does nothing, and the space. This is the
Click it on the other screen.
How about the enter key?
Yeah.
well. uh, I've never encountered this before. So clicking on either screen doesn't work.
Try your arrow buttons on your keyboard.
Nothing at all is working.
Double click enter.
All I can do is stop sharing and start again, and
All right.
stop the PowerPoint, close it all, just redo everything. Sometimes even restarting the whole computer. All right, I'm restarting my PowerPoint presentation, and I'm sharing again.
Yeah, if worse comes to worse, you could simply click on the slides here. We can
Yeah,
see your main screen just fine. So if you want
yeah,
to just click on the next one, we can follow it that way.
yeah.
So you're not seeing it again. Is that
We
right?
see we see your screen and we see it not in presenter mode, just in, normal mode.
So if you click on the next screen, then we'll see the next slide.
Yeah.
It must be a problem with my computer. I don't know. Oh, now it's working. Is it? Are you seeing it now?
No,
We see your screen. Now you've just changed the slide. So yeah.
All right. So you
Oh,
see now brainwaves
no, I lost
recordings.
it. Now we see
no,
your desktop
you
again.
you
The
moved it
desktop.
onto a different screen. Yeah.
We assume that's you rappelling down the mountain. Hmm.
No, that's my daughter.
Oop, now we got
Really,
brainwave.
I'm really sorry. So now what I've done is disconnected the other screen. um, and
We see the second slide now, the one that says brainwaves.
yeah,
Perfect.
Okay, good. Now we see the
yeah. So I just
PG.
disconnected the other screen for some. It is so the problem some problem with my computer. But you're now seeing brainwaves go across the screen.
Yeah.
Yes.
Okay, I can't see the normal Zoom, but I'm going to continue. So again, I'm sorry, there's some problem with my computer, but these are brain waves, and these electrical activity is radiating out of your brain and through your scalp. From the time your brain was formed until the day you die. They're always surging through your brain. They change with your thoughts and your moods, your conscious and even your preconscious thoughts. And right now, everyone listening, all of our brain waves are in sync with each other. But what are they? Who discovered them? And why is the name of the person who made what is, I think, one of the most momentous discoveries in brain science in the last century unknown to most people? And what motivated him? What did he think he had discovered? And what was the reaction of other scientists? And what do brain waves tell us about how the brain operates? I'd like to talk about also the implications of being able to hack a person's mind by reading brainwaves. And finally, what are the facts? There's a lot of misinformation and superficiality about brainwaves, so we'll clear it up. I've advanced the slide, and now you can see a neuron. Is that correct?
That's correct.
All right, thanks, folks. So, the neurons, as we know, communicate by generating electrical impulses, and those impulses create electric fields around the neuron. When populations of neurons fire, that creates a field of electricity in the tissue. It can be picked up by electrodes on the scalp. That's ECOG, and or through on the cortex or on the scalp, and that's EEG. So it's a bit like being able to hear what's going on in the stadium from the ballpark. You can't hear individual conversations; those would be the neurons, but you can get a lot of insight into what's going on the field just by the noise from the stadium. So that's something, an analogy to what brainwaves are. But they're more than noise. They are they actually can change the function of the brain. I'm hesitating because my screen is obscuring part of the information for me. So it's not just a consequence of neural activity, but the neurons fire when the difference in voltage inside the cell and outside the cell reaches a certain threshold. Um, and that can change either by a neuron stimulating a neuron and changing its voltage to make it fire, or by changing the voltage outside the neuron. And that's what the brain waves are doing. Those are oscillating electrical fields. So those fields can inhibit or stimulate neurons to fire. And because it has a brain wave, brain comes in waves, then they have the same properties of waves in other contexts. You have destructive and constructive interference. And so this is a way to couple populations of neurons in the brain together into functional assemblies. So for example, when you have a memory, this pulls together sights and sounds and emotions and smells. Those things are in different parts of the brain. Somehow they all come together instantly. They're not wired together. A new concept of learning and memory is that brain waves are causing these populations of neurons and coding that information in different parts of the brain to come together. So I'll be talking about brain waves can be used to reveal neurological conditions, not just epilepsy, but all kinds of neurological conditions, psychological disorders, and there are treatments available by controlling brain waves. Monitoring electrical activity in the brain allows us to know what you're thinking, can tell what your individual brain can do well and poorly, can predict what you're going to do and meld the mind and machine. I'll talk about a little bit about mind-to-mind transfer and mind control as well. So first, the facts, basics about brain waves. Brain waves come in different frequencies from delta to gamma, less than a hertz, 1 cycle a second up to 100 hertz. And for those who are not familiar with brain waves, I'm sure you've heard of these different waves, categories of waves, but they're not different oscillators in the brain. What it is fluctuations in electrical activity in the brain, much like stock market prices. And so to analyze this activity, scientists simply break it down into how low frequency and how much high frequency activity do you have, and divide that into these 5 bands. So that's what the delta through gamma brainwaves are. And we analyze brainwaves in various ways. One way is to study how brainwaves patterns and intensity change in different parts of the brain, because different parts of the brain carry out different functions. And for example, here is the theta wave activity in the brain. It's very high in this region. And here's the alpha wave activity shown as pseudocolor. And if you take the ratio of those two, the FDA has approved this as a diagnostic indicator of ADHD. Another way that brainwaves are analyzed is by coherence, and that is how much synchronous activity is going on between the electrodes, which represent different parts of the brain. That's actually my brain with a lot of prefrontal cortex theta activity. fMRI is another method that you're familiar with to record electrical activity in the brain. Unlike EEG, it can record activity deep in the brain. EEG only records activity in the cortex, but cortex is a pretty important part of the brain. And it is based on oxygenation of blood, because when neurons fire and they demand energy, then the oxygen gets depleted in that local region of blood. So it can measure activity deep in the brain, but it's very slow. It has a temporal resolution of minutes. Another method is near-infrared spectroscopy, which infrared lasers are beamed into the head. Just like the beam in a remote control, that infrared, it's invisible, but it senses the reflected light and can detect the change in color and hemoglobin. And this now is more like EEG. It can give you millisecond recordings and even deep in the brain. So the first person to record brainwaves in humans was Hans Berger. And he was a German psychiatrist. He worked in former East Germany, Jena, Germany. And there was not a lot about him that was available. So I wondered who he was, what he thought he was doing. And the peculiar thing is that he discovered brainwaves. He did all his work on his mental patients and did it in secret. And he didn't tell anyone what he was doing. And for 5 years after he discovered human brainwaves, he didn't tell anyone what he was doing. So I went to Jena, Germany, to try to get to the root, look at primary sources. This is the hospital where he, in the 30s, became the director of the hospital, Jena, Germany. And when I went there, my hosts was a neuroscientist, Christoph Reddies, and Suzanne Zimmerman is a medical historian. And so we went through Hans Berger's notes his equipment's gone, but all his notebooks were there. And here, we're looking at century-old notebooks. That's, Hans Berger's writing, recording these responses in the brain. And he's using this kind of apparatus, which looks something like a manometer. So this is not EEG. This is very much like a barometer used to measure air pressure. What was he doing? What he was doing is he took his mental patients who had had an injury, a skull fracture with missing part of the skull, and and then the skin had grown back over it, but you had this cranial defect. This is from his notebook, and he put a rubber cup over this cranial defect and attached it to the manometer. And what he got, here is one of his patients, what he got was pulsations. So the brain's pulsing. Of course, it's pulsing because of the blood. He was looking for physiological basis for how the brain worked. So kind of ahead of his time, if you think about it. The MRI basically is the same idea. It's looking at blood flow with cognitive function. So, he had very primitive tools, but he would record these pulsations in the brain, and then he'd have his patients do arithmetic or smell different odors, etc., and see how that changed the oscillations in the brain. So this was published in 1901. But he did not invent this method. He adopted the method. The method was actually invented by Angelo Mosso in Turin, Italy. And he was not interested in brain function, using it for that reason. He was interested in high altitude illness, because Turin is in a mountainous region, and altitude illness causes swelling of the brain. So he had people who had had cranial defects, and he would take them up the mountain and watch their monitor the swelling of the brain and study how different combinations of gases, breathing carbon dioxide, etc., would change the swelling of the brain. And here's one of the patients with this apparatus. So Berger just used this apparatus, but he built a high altitude laboratory. I went there out on Mount Rosa, where he did these research. You had the North Face parasol and the Patagonia tweed jacket, and then he would drag these poor patients up there to high altitude to study their headaches and brain swelling while they breathed different gases. Now, he generated a lot of very interesting and useful data that's on altitude illness that is still very relevant today. Now, at this time, a paper came out by this Nicholas Fayed, a neurologist in Zaragoza, Spain. And he had done MRIs on 13 climbers who came back from summiting on Mount Everest, and all but one of them had brain damage, permanent brain damage. You can see these hyperintensities here look like shotgun pellets. Now, climbers know you can damage your brain, you can die, high altitude cerebral edema, but none of these climbers had any idea that they had injured themselves. Everyone, when you get acute altitude illness, say you go up to a ski resort too quickly and you get a headache, that's your brain swelling. But none of the climbers had any symptoms yet. All but one of the 13 had permanent brain damage. So then he looked at climbers that went to other mountains and found you don't have to go up Everest, Mount Blanc, Aconcagua. The climbers also came back with this. So I'm a climber and I'm a neuroscientist, and this sounded very interesting to me. And so I pitched to Outside Magazine that I would get my brain scanned and then go climb a high altitude mountain and scan it again to prove that you can do this without damaging your brain. Because, what happens, it used to be that people would take weeks or months to climb a mountain, and the body can adapt if you go at that pace. But now people hire a guide and they go up there on a weekend, and the body hasn't acclimatized. Anyway, Outside Magazine liked the idea. They bought, they commissioned the story. And then I found that nobody would scan my brain. I went to hospitals, colleagues. It didn't matter if I paid in cash. Apparently, there's some ethical problem with putting a person in a situation where they could injure themselves just because you'd like to study the injury. Nobody would do it. So I called up Nicholas Fayed and told him what I wanted to do in Spain. And he said, "Oh yeah, sure. Come on over after to the clinic. We'll scan your brain, then we'll go out to dinner." And so that's what we did. They eat dinner at 10 o'clock over there. So first I had to climb a mountain. By the time they gave me the commission, it was already winter. And we had horrendous. Oh, the mountain I climbed was Mount Rainier. A snowstorm. I did it with my son Dylan. And, it wouldn't be a climbing story if there wasn't a near-death experience. I'll just say that I hate crevasses. And then when I got back, I went to Zaragoza. He scanned my brain. There's my brain. And what he said is that it was perfectly normal for someone my age, which I don't know what that means. So this is the apparatus that Angelo Mosso used, and I went to his laboratory, and here's a smoke drum that he used to record these recordings of pulsations. He put smoke on this paper, and then this clockwork turns this drum, and a needle scratches it off. So it was really exciting because I held in my hands the first recordings of activity, physical manifestations of activity in the brain, both this and Hans Berger's recordings. Now, Berger, on the other hand, he was doing this because he wanted to know how the brain worked. And he believed that there was psychic energy and that, like other forms of energy, it can't be created or destroyed, but you can transfer it, and energy, cognitive energy is work, and so there should be a temperature change. So one of the things he did is he took and stuck a rectal thermometer into the brains of his patients and had them do cognitive tasks and recorded temperature changes. So again, this seems very crude, and different IRB ethics today than back then, so we can't really judge it. But he was trying to find a physical basis for mental function, which at the time was, a really revolutionary idea. Then when electricity came on the scene and at the early 20s, he adopted that. He stuck needles into the same cranial defect and then recorded the electrical activity in the brain. He discovered that it was oscillatory. He did his work in secret. And he first recorded him in 1924, and he didn't do anything. He didn't tell anyone what he was doing. So what was the reaction? Well, the reaction from the scientific community was to dismiss it. We were in a phase where a reductionist approach to understanding the brain was taking place. We were looking at individual brain cells, Ramon Cajal, identifying the neuron doctrine, and the idea that you could stick a couple of electrodes on the skull and learn anything just didn't fit with the thinking of the time. And his work got no traction until a Nobel Prize winning scientist in 1932, who was a neuroscientist, took and repeated the experiment on his own brain and said, Berger's right. And he had these alpha waves, which were then called Berger waves. When he closed his eyes, they got larger intensity, and he closed his eyes and they were damped. But then he did the same thing in a water beetle and showed that the water beetle had the same response, sort of dismissing the whole idea, the significance of brain waves, and he never worked on them again. Hans Berger died in 1941. He committed suicide. So I'm at a loss here because I can't see any of you. So let me know if there are any problems. The display is not showing.
There's no, and everything
Okay.
is going beautifully. Thank you.
All right, I'll keep going. Thank you for that. So he committed suicide in 1941. Now, Jena, Germany, during this time was the rise of the Nazis, and mental hospitals were the epicenter of the eugenics movement. Actually, to rid society of the genetically unfit, the so-called gypsies, Jews, homosexuals, and mental patients and people with disabilities. And this was started in mental hospitals. And the actual methods of euthanasia, which is, I don't know what the right term is, it is used in this context, was developed in mental hospitals and then industrialized and put into concentration camps. So Hans Berger would have been right in the middle of this. And all the biographies at the time indicated that Berger was persecuted by the Nazis. He hung himself in the hospital in protest because of persecution of the Nazis. Well, that always seemed a little weird to me because I couldn't imagine that he'd be head of the hospital, you know, during the Nazi rise. Why wouldn't they purge him? Well, it turns out that this was all a whitewash. And that's not, so his biography up until the time I went there was all wrong. But in fact, Hans Berger was a Nazi sympathizer. He served on the board of forced sterilization of all the mental patients in his hospital. And here's a letter from Karl Astel, who ran that program, thanking Berger for his work on running the forced sterilization. And this was after he had retired. So it wasn't like he was being coerced by the Nazis. He didn't have to do this. So what happened is after the end of the war, a lot of the people stayed on in the university in Jena. And so they whitewashed their biographies. And many of them were, you know, they're still there, you know, almost to the time that I went and visited. And this all came about by this medical historian, Suzanne Zimmerman, who got the records after the fall of the Berlin Wall from Russia that exposed all the truth. And one of the things they found out was that the renowned anatomical museum in the Jena University, which is really world renowned, turned out to be the specimens were derived from the victims of the local concentration camp. Once they found that out, they tried to remove all of those and put up a plaque. But you know, the nature of the specimens, they don't know for sure they got it. But Berger was not the first person to discover brainwaves. Brainwaves were discovered earlier on animals, as you might imagine. And they were discovered by Adolf Beck. Adolf Beck was doing this in 1891. And with very primitive instruments. You had a mirror suspended by this filament in a magnetic field, and like a compass needle, if you put an electric field or electricity near it, the needle will deflect. And so he attached electrodes from the brain of an animal, dogs, and various animals, and that would cause this mirror to twitch. And so he noticed this mirror was vibrating, oscillating. And instead of thinking of noise, he realized that the brain has spontaneous oscillations, brain waves, and that it would respond to stimulation and cognitive function, shining a light. So these are not millivolts because these are millimeters of deflection of the light beam projected, reflecting off this mirror onto the wall. And, you know, it's not a laser pointer. It was a candle. So pretty remarkable achievement. He got all the details right. Now, he was doing this work in Poland at the time, in a city of Lwów, where he was chairman of the physiology department. World War I started, and the Russians took the city and changed its name to Lviv, which I think you've heard of, recent news. They captured Beck, and they took him, held him prisoner in Kiev, which was in Russia, and held him prisoner. While he was in prison, he wrote to famous psychologist Ivan Pavlov, the Russian renowned scientist, pleading for him to help intercede and get him released from prison. And ultimately, after a couple of years, he succeeded. He was released. He went back, began to do his work. The next step would have been humans. But then World War II starts, and now not the Russians, but the Germans come in. Adolf Beck was a Jew, an intellectual, and there was the Nazis built a huge concentration camp in the city and exterminated the entire population of Jews in the city. They came to take Beck, and he swallowed cyanide and took his own life rather than have it taken in the concentration camp. So here we have the pioneers of brainwaves, both who took their own lives. One, the victim of Nazis, and the other, a Nazi sympathizer. It's just kind of very interesting how science and society are intertwined. But Adolf Beck wasn't the first to record brainwaves. The discovery was made much earlier. And I can't see it, but 75. And it was so far ahead of its time, it was lost. And Berger didn't know about it, and Beck didn't know about it. And this was done by Richard Caton, who was a physician. He earned his living by taking care of patients, yet he was doing on the side, fundamental brainwave research. And at a time when electricity didn't flow through anything in the man-made world, it's gas lamps and horse-drawn carriages. If you studied electricity, it was like, dark energy today, and you had to build your apparatus. You had to make your own electricity. So it's amazing what he did. He published in the big journals, and then he had an opportunity to come to a scientific meeting in Georgetown, near where I am here in Maryland. And from his notes, he presented his work, and he said that I read my paper on electrical currents of the brain. It was well received, but not understood by most of the audience. So, the fact that he was right, but way ahead of his time, his research wasn't understood, and it was forgotten. And in fact, the reason he came to America to this meeting is that his family came to the United States in the 1600s and established the town of Catonsville, which is 30 minutes from where I live. It's next to the Baltimore airport, where I took off to go all around the world to try to study brainwaves, and had no idea, because there's no information about this, that actually the first person to record them did so just a few miles away. But he got it all right. He published in the big journals, and I think that's really interesting, because that's happening today. Somebody's published something in the journal of science, and it's just so far ahead of its time, people don't get it, and it gets forgotten. By the way, as an aside, it's really interesting. We take it for granted the brain works with electricity, but, how did that discovery get made? And, again, this was when electricity itself was a big mystery. So a lot of this came about by doing research on criminals who had been executed, and then using electricity to try and reanimate them, bring them back to life. And in fact, Mary Shelley had attended one of these scientists' lectures on attempting this, and that inspired her to write the book Frankenstein. Anyway, a little bit of a side, but we take electricity and electrical activity in the brain for granted now. Mind-to-mind transmission. Well, in the 1920s and 30s, seances and mental telepathy were all the rage. Hans Berger was a firm believer in mental telepathy. He wrote about his telepathic experiences, and he thought that maybe brainwaves could be the mechanism of telepathy. He studied that and ultimately found no evidence for it. Others did, though, continue to believe that mental telepathy and brainwaves were related. Most of this is not viable science, but it did fit with the time. Now let's come up to modern times, where we have brain-to-brain transmission. And here what we have is a student watching a video game. His EEG is being recorded, and when he's supposed to pull the trigger on the gun or in the game, that impulse is detected by his brainwave pattern, and that then is communicated over the internet to another building, where another student has a transcranial magnetic coil on his brain, so that when this student thinks of pulling the trigger, this student in the other building suddenly finds his hand clenching and pulling the trigger, transmitting this cognitive response over the internet. So if you can transfer information from human brain to human brain, well, why not to animal brain? So here we have a rat, and we're going to stimulate this time not with electricity, but with acoustic ultrasound. I'll talk about that a little bit later. We have a human here. His brain waves are being recorded. They're being synchronized because he's watching this flashing light that makes the brain waves very characteristic. Now he thinks to make the rat flicks his tail. That's detected and transmitted to stimulate in the rat's brain, and the rat flicks its tail. Mind reading. Well, there's a lot of activity in using various methods to monitor cognitive processes. Here's one example of fMRI, near infrared spectroscopy, I'm sorry, in which to a series of yes and no questions, the answers can be gleaned with 75% accuracy by the cortical responses. They have to be true, false questions. Why are people doing this? Many, many people who present in the hospital in a coma are actually conscious. And how do you know? They can't move, they can't speak, but by using ways to monitor brain activity is now becoming aware that they are aware of what's going on around them in many, many cases. So how does this work? Well, they had these patients. So here's the brain response when the answer is yes. Are you in the hospital? And here it is when the answer is no. Do you feel cold? It's very different. Well, what it is that they told the person to imagine that you are playing tennis if the answer is yes. Now, if you imagine you're playing tennis, this lights up activity all over the brain and creates a big signal. So kind of a roundabout way, but it is a way to get into a person's mind. Here's another example. Even your unconscious or preconscious thoughts. I learned about the work by Howard Poisner, UC San Diego, where they have a supercomputer center. He built this room with the speakers all around, virtual reality helmet, you create this virtual reality environment while he records your brain waves. He's interested in learning, and not conditioned response learning, but unsupervised learning. How do you learn, where the metro station is? Nobody rewards you or tells you. So this is what he wanted to understand, is how the brain learns in a more sophisticated level. So I put on these virtual reality goggles while he's recording my EEG, and suddenly I am transported inside a Navy aircraft carrier. All of his research is funded by the Navy. And virtual reality at the time was very new when I did this, and it was really quite sensational. Suddenly I'm transported inside this ship. I look up, I see girders. I look down, I see, hideous government linoleum. I go into the storage room and I start to walk out, and I can see the planes out here, and says, "Don't go out there, stay in the storage, in the room." And I'm walking around the room. They're watching on a screen, seeing the same thing. And he says, "Well, you're looking for a green balloon, green ball." So I walk over, I find a green ball, I touch it, and it bursts, and inside there's a fire extinguisher. I say, "Good, now go find another one." So again, they're monitoring all this. So I come back and I find another one in a different place, and I touch it, and there's a wrench inside. And what he found is when he took subjects and then came back subsequently, he had switched where the fire extinguisher and the wrench were, so that when the person popped this bubble expecting to see a fire extinguisher, within a fraction of a second, there was a brainwave response that indicated that he had switched the objects. So faster than the blink of an eye, your brain had learned where this object was and that this was in the wrong place. And you can see how the Navy might be interested in, the quickest gun in the West wouldn't even know they had pulled the trigger. But now let's talk about your being able to tell your brain's capabilities, not mental illness, not neurological illness, just what you're good at. Are you good at reading? And are you good at math? So here's an example. Structural differences correlate with how good these people are at playing this particular game. IQ can be determined by EEG. I'm sure you guys know this in many different ways, but here's one I picked. It's interesting because it's sexually dimorphic. The beta wave uh, power during REM sleep correlates with IQ in women, but not in men. Obviously, there's no difference in IQ, but there's this sexually dimorphic difference because you can have a race car with an electric engine or a gasoline engine. You can get to the same performance with different means. So it's interesting. Now, the reason that this is possible is because we now understand the circuits in the brain that become activated while we are doing different functions. I'm sure you're familiar with these. The default circuit when your mind is wandering and you're just thinking of autobiographical information. Now we know what these circuits are in the brain, for example. And so by just putting a person in a room while they're monitoring their EEG while they do nothing but let their mind wander, we can get an idea of how their brain is wired and what they're good at and what they're not going to be good at. So this can predict your capabilities. And I had heard of this neuroscientist, Chantel Pratt, at University of Washington, who said that she could record a person's brain waves for 5 minutes while they did nothing and tell them whether or not they could learn a foreign language easily or struggle. So I challenged her to do that to me. I went there to Washington. She put these electrodes on my head. And then she turned down the lights, left the room, came back 5 minutes later. She starts working up the data and she turns to me and she says, "Good thing you're an American." Which is true. I studied German and Spanish and I tried Japanese. I just not good at languages. Anyway, but this now can be used, for example, because we understand the circuitry involved in these cognitive functions. For example, reading. It's possible to ascertain in a preschool child's brain if that child will have trouble reading or be a good reader, and accurately predict the reading proficiency 3 years later, for example. So think about how that's going to change education. Marcel Just's research is very interesting. He uses fMRI, and he can decode what you're thinking, what number you're thinking of, emotions. He can tell what you're reading. And this is all because when you have a thought, it activates different parts of the brain. If you think of a hammer, that's a tool, it's heavy, it's a whole different thing than if you think of an apple. And so the different constellations of structures in the brain will become activated in these two different concepts. And so that's how, with machine learning, he can begin to read a person's mind. Nothing's more private than the thought, but it's no longer private. Here's a practical application where they show a bunch of pictures of juvenile animals and can detect whether this person is going to be a pedophile because their brain response is different from that of a normal set of brain waves. But actually not brain waves, this is MRI. But, at what point do you determine that a person's responses deviate from the norm enough to start worrying about things? So mind control. Jose Delgado was famous for his stunt in Madrid, where he stopped a charging bull by radio transmission that energized electrodes that he had planted in the bull's brain. So this was a great, demonstration. But he was interested in using brain stimulation to control human behavior. And that's why he picked bulls. He was interested in violent behavior in particular. But, and also to treat psychiatric disorders. We had developed electroshock therapy. The first device used were these stun guns used to kill pigs in a slaughterhouse. And, ECT is still the most effective method of treating depression that can't be treated in any other way. But it's just too crude. It causes a brain seizure. It causes a body seizure. And so Delgado and others today now feel that it's the right idea, but we just need to have precision electrodes and more. This was just too crude, and be able to correct whatever defect is. But he was interested, if you read this book by him, in using brain stimulation to control the masses of violent behavior and psychological problems. That scared the public so much that all the research in this field of brain stimulation ended. It was no longer funded. It was the government wouldn't fund it, and it stopped. And it's only now coming back with things like deep brain stimulation to treat Parkinson's. Well, the physicians are now, since it's approved, they can now use it for other things, and they are now using brain stimulation to treat all kinds of neurological and psychological disorders. And we have better methods, more sophisticated, non-invasive methods, transcranial magnetic stimulation, and used for neurology, psychology, and enhancing memory and cognitive performance. Lasers, optogenetics, ultrasound, transcranial direct and alternating current to activate or inhibit neurons in the brain very precisely. The Army is using this to train pilots, and they use brain stimulation and have tremendously increases the rate at which these pilots learn. And a lot of college kids are doing it, going to Home Depot and making their own direct current brain stimulators to help them cram for tests. There are non-invasive methods. Now here we're talking about something close to your heart, but again, I don't think you're all doing this, but that is using neurofeedback to control, to treat mental psychological illnesses. I heard about the Neurofeedback Center in Virginia. I went there. I met Jessica Ure and Robin Bernhard, and they were using neurofeedback to treat their patients with all kinds of psychological problems. And it was quite effective, but not effective for all. It only worked for about half the people. Then they realized, well, what they need to do is do an EEG first and see if there are abnormalities and how they deviate from the normal, and then use neurofeedback to change the brainwave responses to bring them back in line with normal. So that's what they do now. The first thing is when they did the EEG, they found that half of the people who had psychological problems really had neurological problems. They were having micro seizures in different parts of the brain, and this was completely unknown and not being treated properly. I'm sorry that I'm running late because of all the problems. I actually went there and did neurofeedback and changed my brainwaves. So it was very interesting. I thought it was going to be like a video game where you rack up points, but it's not like that at all. The brain knows what you're trying to do. It's very interesting. Other non-invasive methods have come about since. Frequency of lights flashing at 40 hertz will cause brains to become synchronized, brainwaves become synchronized. You know that can cause a seizure in some people. That activates the immune cells in the brain called microglia, and they consume the toxic beta amyloid plaque. This is now being used in clinical studies for Alzheimer's, being used in people, and very promising. Quickly, brainwaves are very important in sleep. These stages of sleep you go through every night, from rapid eye movement down to this deep sleep, and you go through these cycles several times a night, and you finally wake up. Well, each of these cycles is correlated with specific brainwave patterns. And, so our understanding of sleep really all comes about from EEG recordings. Anesthesia, you hear that you're putting somebody to sleep. Well, it's not what you're doing at all with anesthesia. You're putting them in a drug-induced coma. The brain waves tell us that you actually have brain waves like a person with traumatic brain injury or in a coma. The thing is, how do you know when a person is really under anesthesia? A lot of times people are aware. They can feel pain. They can hear the surgeons cracking jokes while they're being operated on. Now people are beginning to use EEGs to deliver the anesthetic. Right now we use all indirect means, the heart rate and body temperature, respiration, instead of trying to monitor the organ that is really giving us consciousness. So this is something for the future. Now let's talk about brain-computer interface. Nathan Copeland and work done by Andrew Schwartz. I know you saw this picture. I met Nathan. He has 2 implants in his brain, in the sensory and the motor cortex. So when he thinks about moving his arm, he is a quadriplegic. All right, can't move anything. But when he thinks about moving his arm and shaking Obama's hand, this robot arm does so because the computer picks up that intention, decodes it, and activates the motors to make this robotic hand go out, shake Obama's hand. But in the glove, in this robot's hand, there are sensors that stimulate so he, for the first time, can feel Obama's handshake. These are courageous people. I met many of them at the neuroscience meeting once. Here's an example of people with locked-in syndrome. They can't, they're cognitively normal, but they can't move, they can't speak. But by putting electrodes in the brain and telling the person to think of activating a mouse, and they're monitoring the part of the brain where motor is controlled, you can now operate a mouse just by thinking of it, a virtual mouse, and you can use that to type. That was very new when I first saw it, only a few years ago, but this field is really, really going fast. This is using brain waves associated with motor control, but now we're beginning to use methods to look at semantics, the concepts, the meaning, how the brain really uses language. So here's a study in which ECOG was used while people listened to radio stories. The computer picked up the brain signals, and after much repetition, could finally decode what story this person was listening to by the brainwave patterns. They could do it real time with high accuracy. This is a paper that is not out yet. It's out online in advance of print. Just came out a week ago online. And here we're moving to semantics. Non-linguistic representations of the brain. So for language, because if we're going to use this for people who have aphasia and various kind of language problems, they can't necessarily perhaps listen to a story. And so we can't train the computer to analyze those brain responses. So if you see a fire, you see this image, and you see the word fire, those things create the same kind of concept in the brain. And so what this new study will show, it's out online, is that they trained people on silent movies, picked with electrodes and on the brain, and could decode what movies they're watching, silent movies. Then they had language where they gave them a story, listen to a radio program, and they found that the same parts of the brains are lighting up. Not only that, it was not unique to the individual. You didn't have to, previously, you would have to train an individual that have to hear the story 50 times so the computer could finally machine learn what patterns of brain activity go along. Now, because the same parts of my brain light up when I say fire, lights up in your brain, they can now use this across individuals. I'm almost done now, coming to the end. The big application in prosthetics. This is a person who had became a quadriplegic. He was an Eagle Scout. He just got admitted to college, and that weekend he went out to the beach, dove under a wave, broke his neck, became a quadriplegic. I met him, very courageous guy. Now he has these implants in his brain, and this time he has these electrodes on his wrist. The spinal cord's broken, so his brain says move your arm, but you can't get those signals to the wrist. So the computer picks up that intention, activates these electrodes on his wrists, and makes his hand move. That's the idea. Now these are this is not EEG. It's called the Utah array. We're picking up it's implanted 128 electrodes in the brain. And so here, first thing you have to do is train the computer to understand his intentions from the neural responses. So they watch the computer, and you move your hand the same way you see happening on the computer. Well, he's a quadriplegic. He can't move his hand. And so nothing happens. But his brain is telling his hand to do this, and the computer's starting to figure it out. And once the computer figures that out, then it's going to be a control the stimulation of the muscles. This was after the training. This individual had been a quadriplegic for 3 years, had not seen his hand move in 3 years. And now it's moving when he thinks about it, just the way he used to think about moving his hand.
That is so
Actually,
incredible. I'm sorry. I
yeah.
just have to say that. That's so
Well,
incredible.
it is incredible. I can't believe it. And look, here's where he eventually got to. With enough practice, he began to develop fine motor skills, and now he can have more of an independent life. When you're quadriplegic, you can't do anything. You can't scratch your nose. You can't feed yourself. That is the most psychologically difficult thing. And so now he has some independence. Um, but there was something even more amazing and unexpected. And that is all of these patients, these electrodes, they don't last forever. You get scar tissue, they corrode. So after a certain amount of time, they've got to come out. So these people are doing this not to help themselves, but they're doing it for science. So when they took out his electrodes, he could move his hand. That was completely unexpected. I met him at the neuroscience meeting. He was in his wheelchair. Handed him my business card. He took it, looked at both sides. He now lives alone. And what happened is training the brain, making it work, either sprouted new pathways or there were latent pathways there that became strengthened, so that now he does live alone, and he's a paraplegic, but not a quadriplegic. So look to the future. Well, that's pretty radical stuff, having brain surgery. So we'd like to have brain-computer interfaces that don't require that. And so I went and heard about Thomas Reardon, and I visited his company in Manhattan at the time. Thomas Reardon, when he was in high school, he was doing advanced math at MIT. After high school, he met Bill Gates, and Reardon invented something called Internet Explorer. And then after that, he thought, well, maybe I should go to college. And he met the physicist, mathematician Freeman Dyson, and said, "You're just too much of a nerd. You need to, broaden your horizons." So he majored in classics, and he graduated with honors. Then he went into Columbia and got a graduate degree, a PhD in neuroscience. And what he realized is the brain has amazing bandwidth of taking in information. We can take in all kinds of information, but terrible bandwidth on getting out information. The brain has only one way to get information out, and that's through moving muscles. Every way we communicate, moving my hands, typing, speaking, is all motor control. And so Reardon said, well, geez, we should actually take advantage of that. And so he put electrodes on the wrist to pick up signals coming from the brain, so that when you think about moving your fingers, it would sense those impulses in what are called neuromuscular units. And I watched him play a video game. His hand's not even moving. Last year, I was invited to, Facebook acquired them. He sold out that company. And then last year, I was invited to London, the headquarters of Meta, where Meta is all about the metaverse and virtual reality. And with these goggles, where you can be watching a video and Googling in real time virtual reality, you can't be carrying a keyboard around. So Zuckerberg is using this technology where this wristband will allow you to control, the computer that you're seeing on your glasses. And he's also using other methods. He's using EEG as well. It was interesting. The reason they had me there and many other people was they were interested in the ethical implications. They're a little worried about, the ethical implications. So it was very interesting. Anyway, moving on. This is a very neat one. Thomas Oxley, he is a vascular surgeon. And this reminds me of that movie Fantastic Voyage, the first one with Raquel Welch in it, and where somebody has a brain clot and they miniaturize a submarine. They go in there and they blast the clot away. Well, that's what it reminds me of. So he invited me into the operating room where this patient's got a vascular malformation. Here's his brain in real time. He's got all kinds of x-rays so they can see. And what they do is they stick a cannula into, first they do virtual reality so they know how to drive through this guy's blood system. Let me skip that. They stick a cannula in the femoral artery and one in the jugular, and they thread it all the way up into the brain, following the course till they get to this problem. And these two things meet. And I'm watching, this is wiggling like a rotor-rooter drain snake. And they go there and put in a stent. Same thing that you do with a heart, and it opens up the blood vessel. And so Oxley realized, hey, why don't we put electrodes on that? They do this it can do this in an outpatient. And so that's what he has this company. It's now in clinical trials. And you can now put electrodes in the brain anywhere there's reach by the blood system. And the signal to noise is fantastic. You're just on the opposite side of this vascular wall. Finally, we got Elon Musk. Elon Musk wants to add this third digital superintelligence layer to the human brain. And so he has this Neuralink, which is kind of a sewing machine that sticks in these electrodes that has many, many electrodes on each filament. And he takes an engineering approach and says, the problem is we just don't have enough electrodes. So he's now built this thing so that we can now have up to 3,000 electrodes in the mouse's brain. And the problem is that we just need to have this bandwidth. Well, Elon, I think, doesn't realize the biological hurdles. He's just looking at the technology. Let's say you wanted to put a thought in the brain. So let's say you have a circuit of 300 neurons, and you're going to stimulate those 300 neurons to either, move a hand or make an image or whatever, load information in the brain. So let's make it simple. Just say you can turn the neuron on or off. That's too simple. We know neurons have a frequency code, but let's make it simple. So you have 300 neurons. You're going to turn them on or off with these electrodes. How many combinations is that? Well, that's 2 raised to the 300. And as you all know, that's a big number. That's what it's called. Its number is more than all the atoms in the known universe. With only 300 neurons, we have 85 billion neurons in our brain. I hope this gives you some appreciation of the brain. And that's just 300 neurons. We don't care about the sequence. Well, the sequence probably matters. And if you consider the sequence, 80 neurons can be stimulated in different sequences to reach that same number. So I hope that, that really shows the challenge, and I think really just the amazing capabilities of the human brain. So let me sum up that I really think the ability to directly interrogate and manipulate the brain function, is going to transform medicine and change society, education. And electricity is the key, because when you go to a doctor now, he or she does a biochemical analysis of your blood and then gives you a chemical to treat your condition. Well, we're on the verge of psychological and neurological conditions being diagnosed by the electrical abnormalities in the brain and then being treated by precision stimulation. So monitoring brain waves and other methods of monitoring activity in the brain can diagnose in a drug-free manner. Neurological, psychological, we can improve disorders, can improve cognition, And really, the important things that change is how the brain works. You know, this old idea of the doorbell circuit when neuron A linked to neuron B, and that's just way too simplistic. It's far more complex. There's communication going on through brain waves that are coupling populations of neurons together. But it does raise these new ethical issues about reading people's minds, controlling their minds, and such matters are really, you know, stopped all this research back in the early 60s. Um, and if you'd like more information on this, yes, as Dr. Kirsten mentioned, I've written a book. It's for the general public. It's won a couple of awards. So I'd like to thank you all. And again, I really do apologize for all the trouble, but with the technology, and thank you for sticking with it. I'm going to stop sharing so I can see you again here. Thank you.
Well, I can't tell you how much I appreciated that talk, and there are a couple of comments in the chat. I do just want to say, for those of you who need to go, go. But
Yeah.
for those of you who can stick around, there's a few questions, and I'm going to guess that there are some questions that people have that might not be in the chat. So I'm going to start with Vashon Smith says, is it a I know the answer to this is yes, Vashon, but I'm going to say, is it a possibility that a mechanism could work with the muscles in people with Alzheimer's and dementia and help retrain or rebuild the brain there by helping to heal or cure? So yeah, I'm pretty sure the answer is yes to
Well,
that.
I'm sure there can be benefit and needs to be explored. You know, of course, Alzheimer's, the key there is diagnosing it early because, you know, it's a neurodegenerative disease, and once there's the destruction, you know, that there's going to be disability.
Yeah.
So it's a horrible, horrible condition, and but to be diagnosed early, and then yes, we should be able to treat it. And you know, this new research on gamma light, gamma frequency blue light is really amazing. It's so amazing. The results are so amazing that it's kind of controversial because it sounds too good to be true among scientists. But the data are really strong, and it's even being used in uh, the clinic. So, yeah.
Yeah, it is quite profound. Lots and lots of thank yous and people who had to sign off. But does anybody have any questions here that they would like to verbally ask at this point before we adjourn?
I do.
Please.
Uh, since the work of WR has stimulating certain parts of the hypothalamus to induce a relaxation-like response in cats, we have not been able to induce a similar effect that humans experience in animals. So do you think that BCI is the technology that can enable us to elicit that response therapeutically in animals?
I think a big part of, thank you for your question. I think a big part of the problem is that the methods are too crude. Methods of stimulation are too crude. And the hypothalamus is very compact with a lot of different nuclei that carry out very different things. And I'm sure you're familiar with the ventromedial hypothalamic lobe, which is the hypothalamic attack region. If you stimulate that, an animal or a person will go into a violent attack. But what we're beginning to learn about the hypothalamus in animal research is using optogenetics so that you can stimulate very specific neurons in the hypothalamus and get very specific responses. And, you know, it's a really interesting part of the brain because it does so many things. But using electricity is not precise enough. You know, electricity follows the course of least resistance and hits fibers of passage, but optogenetics is neuron specific. But, you know, there are ethical problems of using that technique in humans.
Understood. Let's just maybe one more question, but I think because we've gone so over time, we need to
Yeah. I got to
Yeah.
thank you guys again for sticking with it. I've never had so much trouble, and I think it must be my computer.
Well, you know,
Some update or something just
I don't
crashed
know.
everything. Yeah.
Mercury is retrograde. Who knows? I don't think it is, but does anybody have any other comments or questions that they want to ask or share with Dr. Fields before we sign off?
I'll ask one out of curiosity. It's Joel here. Sorry, my camera's not functioning. I'm having similar issues. I'm just wondering, in BCI, it seems like what's presented and from what I read is a lot of it is about bypassing injury and getting signals to into the brain. But is there research around the brain accessing like auxiliary devices? Like I think you can put on a USB, you can put an encyclopedia on a USB. There's something like that where the brain, people doing work to be able to access offline storage
That's
to
a
expand,
great question.
our language
Wow.
capabilities or,
Well,
things
we
like
have
that.
nowhere near the, thanks for the question. We have nowhere near the knowledge to do that yet, but that is definitely, people are trying to do that. In the future, you just don't understand how information is encoded in the brain. And in fact, a lot of people, and there's a lot of evidence to believe that the big reason that the BCI works is not so much a big fancy computers with machine learning and everything. People think the brain is learning. You talk about, you know, intelligence. The brain is very, very good, and the brain is learning how to work the computer and starting to generate signals that it knows. For example, in Ian Burkhart, the quadriplegic, the brain starts to make the signal that's going to make the hand move. It's not a normal thing. So
Like a natural AI.
Yeah.
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 So it's not anything, we're nowhere near doing anything like downloading information or taking
Wow.
information out of the brain. Really, it's all based on kind of the same thing Amazon does, predicting, the next book you want to buy by just monitoring activity and looking at patterns. But we don't know. I often use the analogy that the BCI works. This analogy may not work for young people. Like driving a car with a clutch. You do that by the sound of the engine, and you know when to shift. There's no actual,
It's feedback based.
yeah, it's
Yeah.
indirect, very indirect. Yet that's how it works.
A lot of our students are
Yeah,
hoping
it's
the
very
download
sensory.
version would be available before they do their final exams, but
Yeah.
like this group's out of luck.
Yeah. Well, but I do think we need to go, but I just want to say, Joel, that
late.
sounds like a great dissertation.
Well, thanks again, everybody. Thank you for the comments, for the opportunity to speak to you, and again, thank you for your patience through
No,
all the
forget about the
failures.
patients. We're studying biofeedback. We walk our talk here. You know what I mean? We're like really chill. Don't worry.
All right.
No, it was awesome.
Thanks a lot.
Thank you so much, and thank you everyone for